Assalamu alaikum wa rahmatullahi wa barakatuh. Welcome everyone to lecture 2 of ITDR1103. Inshallah, we are continuing on discussing about sets. So part 1, we discussed about the basic terminologies about set and how we represent a set and the basic operation on sets. In this session, we will discuss about laws of sets, the power set, order pair, Cartesian product, computer representation of sets, set operations using bit strings. So to start with, laws of set is a group of law that used to illustrate a set. We have the law here and we got name in here. So for example, the first law, as you can see here, when we got a set with double complement. So a double complement is equal to the set itself, and we got this as a double complement name. Let's see this set, which is the following: A union B intersect C. This will equal to A union B intersect A union C, and we call this as distributive law. So those laws of set will be used in order to solve the upcoming problems, and I, as usually told you, they are not need to memorize those laws. All what you need to do is to use it and practice. So we can verify laws of set either using the laws itself, or we can use the Venn diagram. And if you remember, Venn diagrams are one of the ways to illustrate a sets. So the laws of set can be used to simplify a given set, just as we will use the laws of algebra to simplify a given algebraic expression. Let's see an example here. We need to use Venn diagram to illustrate the second De Morgan's law for a set. Now if we go back, De Morgan's law is this law, and we need to illustrate the following: the second De Morgan's law, which is A union B complement is equal to A complement intersect B complement. So A union B complement equal to A complement intersect B complement. So in order to use Venn diagram to illustrate this law, we need first to find the left hand side of our law, then we got the right hand side of the law, and we should have the same Venn diagram. So let's do it like this. Let's start with A union B complement. In order to draw this, we should start with first A union B. So here we got, this is A and B. A union B means all the elements of A and B also. Then we should find the complement of this drawing. So here we got, this is A and this is B. So A union B complement. So we know that complement means if I got all the set in the universal set except what I have in the set itself. So the complement of A union B will be this. Now let's see the right hand side. A complement intersect B complement. First, we need to find the This is A and B. A complement. For A complement is everything except the element of A. Okay, B complement is everything except the set B. Now, A complement intersect B complement is equal to the intersect, so the common element between A complement and B complement, and as you can see we reach at the end that this is equal to this. Alright, now let's use the laws of set to simplify the following expression. A union B complement, complement union A. And in order to simplify the following, we need to use the laws of set. So we search for any law that can simplify whatever we've got here. Okay, now first we will start with the Morgan's law. So we supposed to break the following complement, and if you can see here in De Morgan's law, A union B complement equal to A complement intersect B complement. So by using De Morgan's law, we will got it as A complement intersect B complement complement. Then we got union A. Now we have got here what? The double complement. So here we got double complement. So for the double complement, if we got complement of a complement, then it's equal to the set itself. So here we have A complement intersect B complement complement is equal to B union A. Now we can see here that I've got intersect and I've got union, and we can see that we can use the distributive law, but first I need to have the A union before. So by using commutative law, we can say that A union B intersect A. So we only just rearrange the expression that we've got here. Now we can use the first distributive law. If I got union and intersect inside, then by using the distributive law, this will be equal to A union A complement intersect A union B. Now we can see that if I got A union its complement, what does give us this result? A union complement will give us U, which is the universal set. So by using the inverse law, we can see that A union A complement is equal to U intersect A union B. Now anything intersect U. So here we got A intersect U equal to the set itself, and this is the identity law. By using the identity law, we know that A union B intersect U is equal to A union B. So we reached here the simplest form of the expression that we got here. All right. Now we are introducing a new topic under sets, which is the power set. And the power set, to understand it, let's suppose I got A equal to A and B. Now, how many subsets I can get from A? So let's do it together. The subsets that can we get it from A is A, B, AB, and the empty set. Now, the set of subsets called as the power set, and we usually write it as PA. Now, the power set of set A is, it will be set of the subsets. And as you know, we need to draw the curly bracket for any set we are got. So this is the power set. And if you can see that the elements of power sets are sets themselves. All right. Now the cardinality of a power set. So cardinality is the number of elements in a set. For example, if A equal to A, B, C, then the cardinality of A is equal to 3, which is the number of elements in my set. Now, if we want to find the power set of A that contain A, B, C, this will be equal to A, B, C. Then we have AB, AC, and BC. Then every set is a subset of self. So A, B, C, and every set has a empty set as a subset. So if we are checking the number, the cardinality of power sets, you can see here that they are 1, 2, 3, 4, 5, 6, 7, and 8. So the power set of set A is equal to 8. And 8, if we're trying to connect the cardinality of the power set and the cardinality of the set itself, we can find that it will be equal to 2 to the power 3. So the cardinality of our power set is equal to 2 to the cardinality of the set itself. Again, if cardinality of A equal to n, then the cardinality of the power set is equal to 2 to the power n. And this is our rule. Okay, order pairs. Now, when we start dealing with sets, we knew that in order to write a set in enumerated form, then we have it as set name equal to curly bracket, then my element. So if we got it as 1, 2, 3, then this is equal to 2, 1, 3, which means that in a set, order is not important. All right. Now, for the order pair is when I have first a circle bracket, then we got 2 elements. This is the order pair, 2 elements. So for example, 1 and 2. Now in order pair, 1 and 2 is not equal to 2 and 1. Okay, so 1 and 2 is not equal to 2 and 1. Something like password. For the password, you know that if you change the place of any digit in the password, then it won't be the same. Yeah? So the difference between the order pair and the set, or whatever we have learned before, is the type of the bracket. In order pair, we have the circle bracket or the round bracket, while in sets, we've got the curly bracket. Alright? Now, sometime we might get n-tuples. So for pair, we know that they are 2. But for n-tuples, they might, if we got 3 tuples, then my order pair will be look like A, B, C. And it can be more than 3. So it might be x1, x2, until xn, based on the number of tuples we've got here. Now, why we introduce the order pair? We introduce the order pair to find the Cartesian product of 2 sets. Now, the Cartesian product of set A and B can be written as A cross B. And this is equal to an order pair that has 2 elements, where the first element is from the first set and the second element is from the second set, which is basically is not equal to B cross A. So, for the Cartesian product is a set of all order pairs where the first element is an element of the first set and the second element is an element of the second set. Alright? Now let's see this example. If we got that A is equal to 1, 2, 3, and B is equal to P, Q. We need to find A cross B. So as we said, if we got A cross B, then it will be set of order pair where the first element is from A and the second element is from B. So A cross B is equal to 1P, sorry, one more time, 1Q. So it's something like I take the first element and have it with the second set, first element then the second element. Then we go for the second, which is 2P and 2Q. Then we got 3P and 3Q. So if we can see here the number of order pairs in our set. So here we got A cross B, the cardinality of A cross B. Here we got 1, 2, 3, 4, 5, and 6. And if we are trying to connect between the cardinality of A cross B and the cardinality of A and B, so let's check. Cardinality of A is equal to 3, which is we have in A 3 elements, and cardinality of B is equal to 2 elements. So 2 is equal to 3 times 2. And from here we can find that A cross B cardinality should equal to cardinality of A times cardinality of B. So the Cartesian product is not only when we have two sets, it might be with n sets. For example, if we got A cross A cross A, so this is 1, 2, 3, and we might get it until an, then the results of the Cartesian product will be a tuple of n elements, which is, let's say, x1, x2, x3 until xn, where x1 is an element of a1 and x2 is an element of a2 and x3 is an element of a3, and we'll do so until xn is an element of an. And of course the elements here depend on how many sets we've got. Furthermore, Cartesian product can be on the set with and itself. So for example, if we got a set that has two elements, which is 0 and 1, and we got it as a square, then this means that the set is in Cartesian product with itself. So by doing the Cartesian product, then we'll have the order pairs as 0, 0, 0, 1, 1, 0, and 1, 1. So we might get it as, for example, another example, if we got two sets, A and the second set is B, then we might have it as A squared times B cubed, which is something like A cross A cross B cross B cross B, and we got the tuple. Now the tuple will be how many? 1, 2, 3, 4, 5, 6. So it will be A1, A2, B1, B2, B3, and so on. Now the last part of our session today, which is the computer representation of sets. To enable computer to handle sets, we assume the elements of universal set U are listed in definite order. So if we got an n elements in U and set A, now the set A will be represented of n bits, the same number of the elements of our universal set. So it will be B1, B2, B3 until Bn. Bi will be equal to 1 if ith element of U is in A. Otherwise, Bi will be equal to 0 if the ith element is not in A. Let's see this example to understand more. Let's suppose I've got U as equal to A, B, C, D, E, F, G. Then, in order to find the representation of D, F, A, G, first thing you need to put in your mind that the numbers will be equal to 1, 2, 3, 4, 5, 6, 7. And then we ask, if the element is in the universal and the set itself, then we write 1. Otherwise, it will be 0. Starting with, is A an element of A? Yes, it is. So we write it as 1. Is B is in our set here? No, it's not. Then we got it as 0. C, also it's not, 0. D, yes, it is there, 1. E, it's not there, 0. F, it's there, 1. And G is there, also 1. Now, let's see. We've got the set represented by the bit string and we need to find the set itself. So, we will go through the universal set. Whenever I have 1, then the element is there and we should write it as a set. So, 0 under 1, under A, so A is not there. Then we got B, C, because I have 1, and D, because we have 1. Then E, got a 0, so it's not there. F, 1, and G, also there. Okay, now we saw how we represent a set in computer. Now let's see how we can represent these sets operation. And as you remember, our set operations are union, intersect, complement, and difference. Now the bit string of A union B will be 1 if the bit string of A and B both have A1. Otherwise, it will be 0. The intersect, it will be 0 if the bit string of A and B both have a 0. Otherwise, it will be 1. So this is the OR and this is the AND. The bit string for a complement is whenever it is 1, then it will be replaced by 0, and whenever it is 0, it will be replaced by 1. And basically, we are talking about the NOT operation. Let's see this example here. We've got the bit string of A and B, as you can see, 0 to 1 1 0 1 1 0 1 0 1, and B we have 1 1 1 1 0 0 1 0 0 1. Then we need to find the bit string of A intersect B, A union B, A complement. For A intersect B, as we got in our rule, it won't be 1 unless both of them are 1. Otherwise, it will be 0. So here we got 0 and 1, 0, 1 and 1, 1, 1 and 1, 1, 0 and 1, 0. Then we have 1 and 0, 0, 1 and 0, 0. Then we have 0 and 1, 0. Then 1 and 0. So here we got 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So here we got 1, 1, 2, 3, 4, 5, 6, 7. 1 and 0, 0, 0 and 0, 0, 1 and 1, 1. Okay, A union B, so we'll start one by one. 0 and 1, 1, 1 and 1, 1, 1 and 1, 1, 0 and 1, 1, then we have 1 and 0, 1, 1 and 0, 1, 0 and 1, also 1, 1 and 0, 1, 0 and 0, 0, 1 and 1, 1. So in union, whenever there is 1, we'll write it 1, otherwise it will be 0. For a complement, so it will be the opposite. So when I have 0, I write it 1. When we have 1, we got it as 0. So this will be 1, 0, 0, 1, 0, 0, 1, 0, 1, 0. The opposite. Alright, just to make sure that this is right, let's do it again. 0 and 1, 0, 1 and 1, 1, 1 and 1, 1, 0 and 1, 0, 0 and 1, 0, 0, 1 and 0, 0, then 0 and 1, 0, 1 and 0, 0, 0 and 0, 0, 1 and 1, 1. So here we reach the end of the first topic of lecture 2, which is sets. Thank you so much. See you in the next session, inshallah.